we only have 2 more classes, and so I have done my best to structure this course around the things you guys seem interested in and that I seem interested in. There's a Venn diagram there, so I've been leaning into that, which means that we are not going to make it through every single piece of the solar system, but I think we've made it through the perhaps most relevant ones, at least in terms of making a story about solar systems in general, which would be great. And in terms of understanding our local environment, which is kind of like where we live, the planet that we know the most about, the ones that we might be visiting or even colonizing in the near future. And so the last piece of that puzzle, particularly as it relates to solar systems in general, is Neptune's. Uh, and so that's going to be the last class that we explore, the last class of planets that we explore today. And then Thursday, we'll put a bow on this whole thing. Before we get to that, we talked about life last time, and I want to make sure nobody has any burning thoughts after that discussion. Yeah, great. Yeah, sure you do.
Later. But I just wanted to know how your wife was so in love with what she knows and what she learns, and I appreciated that so much.
Oh,
You as well. But when there's a lot of professors that talk about certain things, and then even if they're kind of there to teach,
mm,
they're like pushing the love out to their work.
yeah, yeah. Well, it's hard. Yeah, I was actually telling I was telling Corey before class, if I had my way, there would be a different guy who came in here at the end and evaluated you guys. It's kind of a shame that the teachers have to do the evaluation as well. It seems like we're not too well cut out for it. So I mean, honestly, both Anastasia and I have a terrible advantage because we don't really do much of this. So our lives don't depend on it, and we're not teaching, 50 or I don't know, 50 hours or whatever most of these professors are teaching. It gets really, really tiring, and you're just processing students. And yeah, it's hard to be a full-time teacher, I think, honestly. So we're lucky because we don't have to do that. Um, so yeah, I'll pass that along. I'm sure she'll appreciate it. But yeah, my wife's awesome. It's true. Yeah, she's a much better biologist than me too. Uh, what else? What about life? You guys getting any closer to figuring out what life is exactly? That's something I was playing with all morning. Yeah,
It's an experience.
an experience.
Yeah.
It's closer. Yeah, it's closer. It's getting in the right direction. Yeah, there's something to that. What else? Any thoughts or yeah.
Down here, did not have life without existence, yet existence how life is possible.
Yeah, I mean, if you define existence as just stuff that has a location in the universe, yeah.
I mean, that's gets real philosophical real quick. I mean, does the universe exist if nothing is around to observe it?
Well,
That's like if the tree fell down.
Yeah, no, exactly.
yeah,
It's like, well, yeah, it does because
I would go with yes, but I know people would push back against that. I mean, it's difficult to evaluate, of course. Uh, yeah, I mean, the value of a theory ultimately, I suppose, is what it lets you do. Does this help you organize reality, or does it disorganize reality for you? Uh, Yeah, I'm not sure some of these Zen like approaches organize reality very well, but that's just my personal opinion. I don't know. What do you guys think? Yeah.
Piggybacking off of all that, I kind of gleaned from last class that life is more the universe experiencing itself.
Mm.
I think that's like a pretty common thought about life in general, that the
Yeah.
universe is just kind of wanting its own feedback. So
Yeah.
life, if there's no feedback.
Yeah, it's a strange tendency. I had this revelation this morning where I was like, I think that the problem here is very similar to when people first started studying magnets. And they were like, they had these things that, like, there's probably one around here somewhere. Like, I don't know, stick, like they had a magnet and they were like, this thing is crazy. You can stick metals to it. And they were like, yeah, it's a magnet, metal sticks to it. But eventually, over all of these experiments with electricity and running currents through wires and stuff, people started to realize that magnetism was a bigger concept that was at play in almost every single piece of matter. Like atoms all have magnetic elements to them. They behave magnetically by degrees in different ways, right? So the thing that the magnet does is analogous to the thing that cells and beings like us do, right? We do life, like we exhibit life. The magnet exhibits magnetism, but the the magnet isn't the only thing that exhibits magnetism. And I think life's going to turn out to be something like that too. The better that we can define the concept for ourselves, we might see elements of life where we don't expect them because they're not the full magnet yet, if that makes any sense. There might be tendencies towards what we would consider life that are not fully functional cells yet. And I think that's the spearhead of origins of life research, of evolutionary biology research, of searching for life on other planets. It really comes down to like, we don't really have a very good, clear definition for what this life stuff is. Like, what does it mean? Is it just cells? Is the magnet the only thing that has magnetism? I don't think so. But we have to develop that idea much further than we have already. And that's exciting. I just think it's very easy at any stage in the history of thought for people to think that they've got everything nailed down because they put a word on it, and it's just the first step in some sense. Yeah.
Really like I think it might have come from you, the explanation or definition, whatever you call it, where life is um, the universe moving away from equilibrium in some fashion, right?
It certainly is chemically.
Yeah.
Yeah, because if your chemicals go to equilibrium, you're dead.
We also call it like moving uphill.
Yeah, 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 yeah.
I thought about uh the life is complexity and abundance quite a bit after last class. And it kind of led me down a rabbit hole of the like how, in recent times we view science as antithetical to spirituality slash religion, but more so spirituality as an idea, which is only in the last 50 years, really, maybe 100. The the like
Scopes monkey trial.
yeah,
Yeah.
but the idea was that I found constantly was there's always some person who's religious is like, but how could God make something that would not be this perfect? Or when you brought like the perfect circles, how could it not be? How could it be slightly not perfect?
Yeah.
All these things.
Yeah.
There's in I found this argument about when it comes to like the Abrahamic religion specifically, from my experience, Judaism, the thing of evolution and how it's the argument that the dark that like the you know theory of evolution somehow discredited the creation, like the whole young earth creationist sort of idea, right,
Mm.
which is really recent, um is it's so easily disproven by one simple thing that is said, and that's in most religions generally. It's a constant idea, which is a day for a non-human entity, a god,
Mm.
is like a thousand years for us,
Okay.
and a thousand years for us for them could be an hour. Or
Okay.
like that time is not necessarily that time was relative, which is odd that so many religions point to, oh, time is relative.
Mm.
When
Mm. Mm.
eventually, we're like, okay, well, actually, time isn't relative, and then we find, oh, well, actually, it is
Yeah.
relative.
I think there's a lot of really good ideas in these methodologies for sure. Even ideas, it's kind of like science fiction too, can sometimes point to really cool stuff. Yeah.
If you think about like the concept of like Buddhism and like reincarnation, I've always like I like connect it to like atoms and like stars and how like they charge each other and then that can be considered life and then uh they die, so they lose their charge and then they move on and
Recycle it.
so it's that circle of like rebirth, like reincarnation and how like everything's kind of like being recycled. So I mean even though like life isn't like present, like imminent. It's still there. It's just kind of like it exists, but it's waiting. If that makes sense.
And so like I have this idea of life might have a an intuition is one way I guess you could put it towards the truth, even if it doesn't fully understand it. Like intelligent life. There are so many of things like fiction or religion or just things where we create that mirror uh, the truth, but are not actually related to a knowledge of it. You know, we talked a lot about like how they saw the stars or the skies and the wandering planets and all this, um, and how there is some truth
Yeah.
to these fantastical like ideas.
Yeah. Yeah. Mars really does seem to go backwards in the sky. It is true. Yeah, truth is a funny, funny word. In terms of this divergence of science and religion, it's really funny because I think in some sense the strict evolutionists walled themselves into a corner where if you read Darwin's Origin of Species, he mentions 7 times the concept of the species striving towards a different future, which is really interesting because eventually, by the time that the molecular people have showed up and the geneticists and all of this, the concept of striving and determination and beholding a future and moving towards it has completely disappeared from the discussion of life as an evolutionary process. Which I think is a pretty silly thing to do because talk to anybody who's alive and most of their life revolves around how they're going to organize their environment to be different in the future, and that's pretty much what life is, right? Is getting everything in order and striving for some ideal version of yourself. And it's probably a little bit silly to treat humans like we're not alive and we're exceptional or something. It's probably so that almost every organism is doing some version of that. And so in some sense I feel like in a effort to wall themselves off from superstitious religious fundamentalists and literalists and all of this, they kind of backed themselves into a corner where it's just gunk crashing into other gunk that determines all of the outcomes, which is just, patently inadequate for a discussion of life. But again, I don't think you're going to be able to have a good biology, that is a scientific study of life, if you don't know what life is. Like, what are we doing? Because right now, biology has envy of physics and chemistry. It thinks we have to do everything in terms of physics and chemistry. And it's like, you guys aren't physicists or chemists. You're doing something else. You're going to need different tools for it. You're going to need a different language. You're going to need a wholly different approach. But it's not going to be possible until we really understand what that phenomenon means. Like, what is it? What is it that is special about this process that defines it and separates it from other processes like chemistry and physics or anything like that? So I don't know. We're just kind of in our infancy with this stuff. It's fine. There's a lot of work to be done. I think that most scientists, all the ones that are on people's high school science class walls, the heroes of science, most of them are religious as well. That kind of escapes people, I think, because I don't think that those guys and gals really saw there being a conflict between mythological perspectives on reality and literal, physical, mechanistic interpretations of how. You know how they saw it? They saw it as the mind of God. They were like, if we, like Newton, he's like, look, the way that I'm describing how this process unfolds, the forces that are being, that are related to the masses and the distances between them and all this stuff, it's just, we're understanding the mind of God here. It's not so much antithetical to religion. It's more just, how is the universe making this happen?
It's interesting because there is this tendency at let's say all of the scales of life that we can study, uh, this tendency toward organization and then specialization and then abstraction, right? Where, even if you look down at an individual cell, you have these proteins, these enzymes that are creating an infrastructure of some kind that are supporting the sustenance of just that one cell's life. But then these cells get together and they multiply and then those cells specialize and they're creating these you get this sort of trend all the way through multicellular life and macrobiology of organization, specialization, and then abstraction,
Yeah.
which kind of brings us to right here, right? Like
Yeah.
we are all conscious
Yeah.
beings, but we don't we are layers and layers and layers of this same tendency of
Yeah.
life to create these abstractions
Yeah.
of itself.
Yeah. And what are they doing though?
Yeah. How do we know
What
it's
are they doing?
the center?
Yeah. Well, I would I would assume they are, but but like, what is all of this stuff doing? Like, what are life forms doing? Like, for me, it's kind of obvious. They're doing what they want to do. That's nowhere included in the evolutionary theory of biology. It's like, you know, the fact that there's will and striving and desire and purpose and all of these things are obvious to anybody who's half awake, but they don't make it into the discussion for whatever reason, especially at lower organisms, single cells and stuff. Yeah.
I thought about how, you described, the world as incredibly structured and ordered, and life in a similar way. But I thought it was interesting that as science became incredibly secularized and the evolutionists cut themselves off, there was this idea that life could only be chaos. That there could not be an order to it.
How so? I don't follow that.
Well, because okay, if for instance, if um if evolution is, for instance, there's the what is it, survival of the fittest, right? That whole idea
Yeah.
that they equated nature to anarchy in its purest form.
I see. But some order emerges out of that chaos. Yeah.
But I think it's interesting that this there's that inherently life is not can't be just chaotic or just ordered. It
Yeah.
seems to be ordered things doing causing chaos,
Yeah.
and then doing order, and then creating order.
Yeah. I mean, you could actually, I've read several approaches to defining life mathematically in terms of the most efficient chemical reaction at disordering the environment possible. So if you think about the natural tendency of things to fall apart, you put an organism in the room, it'll fall apart twice as, like, exponentially faster. Because organisms just rip stuff up, basically. You eat breakfast and it doesn't come out looking like a breakfast burrito anymore. You know what I mean? It's like you breathe in oxygen, it gets ripped apart. Like this is kind of what life does to some extent, is maximizes the production
All
of.
that like the metabolization of the environment.
I've heard it described as the law of maximum entropy production,
Okay.
but I'm sure there's lots of different variations on that.
No,
Yeah.
that was just your basic the way you described it. It sounds like the organism's like consuming the order and producing disorder.
Yeah, yeah. And that's favorable. You got to keep in mind, like, falling apart is actually easy energetically. So organisms could be viewed on balance as being, although we seem locally expensive in terms of the amount of order and, like, oh, it's so strange that that all this order would happen, that it was something so structured. But it's like, in terms of the balance of destruction and chaos that are caused by creatures being alive,
Yeah.
it might actually tend towards the chaos at the end of the day.
Does that come back to like the idea of this gradient, like gradient
Yeah,
all the way down?
yeah, yeah.
It is in life's nature to create a system that funnels order into chaos in order to derive energy.
Maximize it, yeah. Well, and it usually starts off probably by inserting itself in an existing flow, right? So if we didn't really talk about origins of life, but when people are talking about proposed places where life could appear for the first time, it's always where there's some sort of gradient, It's like thermal vents, shallow evaporating pools, and these metal-rich, nutrient-rich, warm little ponds. All of these are sort of trying to find a place that already has this kind of thing happening. So the life form simply can get a kickstart without having to do any of that. Yeah, it's kind of interesting.
Radiate to
Makes sense though. Yeah, it's like the same way that you would generate. Sorry, I always have to. The same way that you would power harvest, right? So yeah, so if you wanted to get power for your light bulbs or whatever, you need to find a gradient. I mean, it's steam usually in coal-fired power plants or nuclear power plants or something like that. But it could be a running river. You know, you got to find a flow to harvest power off of it. I'm always careful not to say energy generation because energy is neither created nor destroyed. But power is sort of what we make of the energy that's already there. The material in motion is there, and we harvest some of that motion for our own purposes. And I think life forms are doing the same thing. Yeah. So the open question is just kind of, is there a tendency for that to happen before there are even cells? Like, are there is life a larger tendency by which there are pre-life entities or pre-life phenomenon that are, in some sense, appearing before there's fully fledged cellular organisms? Yeah.
I think probably yes, just by the virtue of there being it, like ordered bodies that exist.
Yeah, I think so too. Yeah.
Inherent nature of thing, like this is people have probably heard, all things yearn to converge is
Hmm.
come to come back. Things that have diverged
Mm,
one
mm,
day to come together is
mm, mm.
an old saying, but there's some truth to it in science because like eventually something will join something else.
Yeah, yeah. I mean, there's also probably processes at scales we can't imagine, time scales, size scales.
Yeah,
Yeah,
'cause
there's probably all sorts of crazy stuff that could be lifelike that we just can't see because we're stuck thinking about it as things that cells do,
because
basically.
like atoms join together to make molecules, molecules come together to create bodies. Those bodies come together to create larger bodies.
Yeah. You guys know ever any of you ever heard of this guy named Michael Levin before? He's a really cool dude. He's got a bunch of stuff on YouTube, but he's a professor at Tufts. I've gotten to know over the years. But he's making pretty interesting arguments they're based largely on simulated molecules and stuff like this, but he's done a ton of work. But one of the things he plays with is the idea that actually molecules themselves can display some degree of uh, cognition when teamed up together that doesn't scale just by the number of molecules that you add. So, there's versions of memory and changes in the behaviors that are almost prebiotic and or pre-sentient in the way that they behave. And it's a hard argument, but I think that there's people who are starting to think about it in this way. And yeah, I'd have to do an entire class to break that idea down for you, but it doesn't matter. The point is that people are looking towards whether patterns that we associate with life could exist outside of the cells that we're used to thinking about it in terms of, because unless life's just always been here and always will be here, if life actually originates sometimes, then where's the line, is it just, oh, now it has now there all of a sudden this matter is just exhibiting intentionality and desires and exploration and self-motivation? Like, I doubt that just happens one day, so what are the tendencies that push it in that direction before it becomes entirely evident that it's a squirming little cell thingy? That's a heck of a question, just for the imagination, to even be like conceive of what are those prebiotic tendencies of nature, and if we can imagine them, then maybe again all this kind of circles around understanding what life is, if you ask me. But
we should probably get onto the Neptune.
yeah, let's talk about Neptunes. Um, Neptunes are pretty fun. All right, so Neptunes. I really want to start working towards a discussion about the formation of solar systems in general. So that's kind of more what this is going to be about. A Neptune is really not that different than a Jupiter or a Saturn. It is the kind of cold, fast truth of the matter. It's just a bit smaller. So The standard story is that a Neptune is a planet whose atmosphere never got heavy enough to kind of compress itself down. So it didn't collect enough goods in the standard model of formation. So to recap the standard model of gas giant formation, the basic idea that people have been saddled with for almost 300 years now is that the stars and the planets all form in place together in one more or less coordinated dance together, let's say. And depending on where they're at in that big cloud of dust and gas that's sort of collapsing under its own weight, depending on where they're at and the particular instabilities of that and how much metals are available, you get different types of stars, you get different types of planets that congeal out of it. Um, so depending basically on how fast that whole thing goes down, how big the core is that it starts out with. By the way, in the standard model of planet formation, they all start off as cores. One of the reasons that I've been kind of throwing alternative ideas at you about this is because the formation of our ultra-dense core is a pretty difficult astrophysical problem to get to the bottom of. And I'm personally not satisfied, and I know a lot of people aren't satisfied with the explanations. So you basically have to do backflips to make these really heavy cores. But once you have a nice heavy core, a big rock, what basically looks like a rocky planet like the one we're on right now, it's pretty easy to stick it inside of a huge ball of gas and have it glom on gas onto it. Now, if that happens really, really fast, it can glom enough gas that it turns into a Jupiter. If it happens kind of slowly, maybe it's a little bit further out and colder, you get something that looks a little bit more like a Neptune. Now, okay, so this is one pathway that we're dealing with. There's some obvious modifiers to that story too that I want to get into, but let's talk about the primary differences in appearance. So obviously, these are our Neptune-like planets in our solar system. We got Uranus on the left there, Neptune on the right. Yeah,
Isn't Neptune less deep blue? Like,
I think it's the other way around. Pretty sure that I got that right.
Yeah, Neptune's on the right.
no, I know that they are like generally. I just mean that like uh Voyager, when it first took a picture of, I believe, Neptune, they oversaturated that.
Mm.
Get another like photo,
Interesting.
and then we did, and it was like, oh, it kind of looks more like Uranus.
Interesting. Well, let's talk about why it's blue at all. That's a really interesting question. So, why is the sky blue?
Raleigh scan.
Rally scattering.
I think
Just like
What's our sky made out of for the most part?
oxygen.
Nitrogen.
Nitrogen, actually.
73.
So, these guys have a ton of nitrogen too, which is quite fascinating. It's in the form of ammonia, which you guys are probably well acquainted with the smell of from like household cleaning products and stuff like that. So the really interesting difference between these guys and the gas giants that we've looked at, gas giants we talked about, they're not actually made out of gas, whatever, we still call them that. We're going to be talking about a class of planets today called super Earths. They're nothing like Earth. They're actually much closer to these guys, but we'll deal with that in a second too. There's all these words that are just kind of broken, but we roll with it. These guys have much more they have a much their atmospheres are enormous. First of all, if you want to call it their atmosphere, they have a core at the center, which is on the order of the size of rocky planets in general. Just like the Jupiters and Saturns are thought to as well. Of course, no one's ever been there. But the main difference is these guys are blue and look different because in some sense they're a more enriched version with more complex chemistry than the Jupiters and Saturns. So, one way to make a Neptune-like planet is actually to cook down a Jupiter, actually. So there's places in other solar systems where we actually see this happening, where Jupiters are drifting too close to their host star, and you can actually see their atmospheres blowing away. And sure enough, their chemistries and so forth are tending towards this kind of phenotype. So that's one way to do it. That's not the standard story for our solar system, of course, because any guesses? Yeah?
The time required.
Yeah, there hasn't been enough time. Okay. We'll come back to that on Thursday. But what I want you guys to understand is that these guys have uh, more or less the same linear. They're on the sort of continuum with the Jupiters that we've already talked about at length, but they got some really cool, complex chemistry that's going on, which is in some sense could be thought of as a marker of having been either heated or having taken longer to form. So, like I think I mentioned this before, but my advisor pointed this out to me, and I thought it was really brilliant. He was like, "Look, heat is basically just speeding things up." I think that's a good way of thinking about it. It's like when things get hot in nature, they sort of it accelerates whatever processes were going. Now, obviously, you take that to an extreme, you can scorch and burn and blow away atmospheres and all of that. But you do accelerate these chemical processes, and so the result is we got water, ammonia, methane, and all of these are at intense pressures. They're basically they're basically under so much pressure that nobody knows what kind of phase they're at. Are they ice-like? Are they liquid-like? It's 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 unclear. They're in a state of matter that we don't easily achieve on Earth with these same chemicals, which is strange. So I think that the popular way of referring to these guys at this point is ice giants, although it's not like solid bricks of ice like you might see in, you know, your drinks at a restaurant or something like that. So I think it's also worth pointing out that until basically the 1990s, these guys weren't really even considered a different kind. They were just called gas giants as well. This whole concept of understanding the chemistry of what's going on has been a hard-won battle. And so this is all such, it seems so standard to you because you all pretty much grew up with understanding a lot of these things, at least roughly the way people talked about them, but it's all very, very new. And there's a few more shocking pieces of this, especially when we start looking outside of our solar system. So inside of our solar system, you can see that they're way out there. Uranus is the next one out. These things orbit so slowly. I'm talking about on the order of 100 plus years, right? Their year takes more than a century for us. I think it's on the order of 150 years for these guys. Let's look at the way that we think that they're organized. So I kind of pointed this out already, but the feature that's quite fascinating about all of these bodies is that they have this core thingy, which is really, really similar to the core of our own planet. Um, they have a sort of mantle or an interior portion which has much more complex molecules. And then they have this kind of hydrogen helium envelope, which is basically what Saturn and Jupiter are primarily composed of, is this hydrogen helium envelope, right? This atmosphere of really light molecules. We're going to be talking about these super Earth type planets here in a second as well, and Earth-likes. And what's really, really kind of crazy about all of these is that, you know, you have a bigger core inside of these Jupiters and Saturns, at least theoretically, but it isn't that much bigger, particularly by size. Its mass might be a lot bigger. In other words, it might be a crunched down version of the same material. But the size of these cores isn't really particularly astounding. And there's a reason for that we're going to look at, because I think what people thought was when they started going and looking for other planets and other solar systems, they thought, okay, we've got in our solar system these Neptune things, and we've got some rocky planets in the interior. We'll probably find a bunch of stuff that's in between sizes, right? And to a certain extent they did, but they didn't find in-between sized rocky planets, which is really, really quite interesting. So rocky planets don't really get that big, is the funny piece of the puzzle.
Something that's been bugging me for a little while with regards to this, and maybe this is a good time to talk about it.
Yeah.
Does the standard story for our solar system formation account for the existence of these complex and heavy molecules in the first place?
Yeah,
Were we born out of some, the like some supernovae that some kind of nebula that then everything just started differentiating into these pockets to form these planets? Because we see inner rocking planets have a lot more iron, a lot of heavier stuff, which is closer to the gravitational center, right?
they have it more concentrated. That's what I'm trying to get at here. That's
Yeah.
kind of fascinating, right? So these guys, if you just look at the cores of all of them, they're kind of the same. At least they're in theory. No one's ever been to any of them. This is all based on a lot of other indirect evidence. But when you look at, say, how much nitrogen is in Uranus versus Jupiter, it's not that much different, actually. The ratio is different, though. So Neptune and Uranus have lost all that light stuff. They've lost like many Earths worth of helium and hydrogen. So they've kind of cooked down to where the only thing left are the heavy stuff, like the nitrogens. And presumably, this happened in such a way that they recombined to make some more complex chemicals along the way, like the ammonium and the hydrogen.
I guess that's what I'm asking. Is like, does the standard story say that these chemical processes are happening in either some kind of metamorphic way on the individual planetary body, or is it a residual compounds that existed before and were disseminated and redistributed?
So the molecules, so molecules are just combinations of atoms.
The atoms, yeah.
Yeah, the molecules, they happen during the formation of the planet in the protoplanetary disk,
Okay.
according to the standard model. They also happen for other Neptune-like for other planets, not ours, but for other ones. We see them happening because of processes like photoevaporation from other stars, core-driven accretion. That's when the core is really hot and it's cooking off the atmosphere. So these kind of cooking processes can also lead to the appearance of complex chemistry and the appearance of, cooked down Jupiters. We're going to talk about cooked down Neptunes here eventually as well. So there's two paths to do it, basically. The astronomers at present are convinced that our Neptunes formed in situ, essentially, right where all the complex chemistry occurred due to its location, and that it didn't have this runaway gas accretion that the Jupiters did and stuff. They formed a little bit slower. By the way, by slower, I just mean on the order of some millions of years. Very, very fast, actually. So, sorry that's not a straight answer,
No,
but
that's okay.
that's the funny thing about this kind of these two paths to make a planet are very much acknowledged by mainstream planetary scientists and mainstream astronomers. They just don't go the whole distance with it, I suppose. But let's just keep that in the back of our heads for now, because there's a few things I want to make sure that we get on the table today, because I think on Thursday we can compare and contrast these two approaches to explaining how a solar system forms. Yeah, no, I mean, they're really important. These are important questions. You can keep asking for sure, but I want to make sure that we understand the two processes that are possible as well as we can along the way. By the way, I'm not going to have too much time to talk about the peculiarities of our Neptune-like planets, which is Uranus and Neptune. They are pretty weird, though. Uranus is flipped on its side. Again, for me, these speak to something very discrete and catastrophic having happened at some point in the past. You see the plane of the ecliptic that everybody else is orbiting on. We're, of course, tilted a little bit to the side. Uranus tilted completely on its side. Neptune is tilted by what, 40? I guess it doesn't have the offset, but its magnetic axis is also offset, which is even stranger. I think for me that speaks to something about its inner core being tumbling in a different way. So these are very strange features in our solar system. I think the only other one that's weirder is perhaps Venus being on the correct axis but going the wrong direction, which is quite interesting. I don't necessarily have much to say about this other than it's pretty cool and weird. But all right, let's get back to let's get back to our formation possibilities here. Um, so people started studying. Maybe I put these slides out of order. Let me go to something else really quick. I'll come back to this. All right. So in terms of understanding solar systems in general, uh, there have been two major surveys. One of them is underway right now. Um, the first one was actually this Kepler project. Um, and then the new one is actually this TESS project. And the Kepler one only looked at one little tiny region of the sky. And it was essentially looking for um, the transit events. So looking how stars dimmed and trying to correlate planets to the dimming of these stars. And then you can come back with ground-based telescopes as well and look for, say, the wobble of the star, which is a process we'll talk about how to do next semester. I don't know if any of you guys will be able to stick around, but we'll get into how all of these measurements are done then. The point is, we're looking for shadows of planets essentially going by stars, and then we're digging out what we can find from it. And so what did they find this, by the way, is like 10 years old or something, maybe a little bit more at this point, but this is pretty new stuff. What did they find? Well, they found pretty much, what they expected they would find at first. They found a lot of Jupiters. They found pretty much everything in between, Neptunes. But they found, let me go ahead and pull this ahead. This is kind of the distribution of what they found. So average number of planets per star versus planet size. So what did they find? They found that the Jupiters are kind of rare. They found actually that the little guys are pretty common per star. But they also found that the two most common sizes of planets are completely absent from our solar system. So planets that are between the size of Neptune and Earth are the most common planets that we see when we look out at other solar systems. Now, let's think about that on its face. First of all, I'll be honest with you. There's a legitimate possibility that the periodic dimming of stars has nothing to do with there being planets there. I know that's really an unfun possibility. But if we take this seriously and we say that the dimming of these is actually representational of planets, then the planets that we come up with have this distribution. So this is weird because I think this was the first time that people started thinking, wait a second, maybe our solar system isn't typical of how solar systems are throughout the cosmos. This is really, really difficult fact to wrestle with. Why don't we have a bunch of these planets that are between the size of Neptune and Earth in our solar system? So next thing they realized was that they looked at the order of the planets in all the other solar systems. And they came up with a few bins, ones where the big guys are at the interior, ones where the big guys are furthest away, ones where they're all the same size, and then us, basically, where it's just kind of a grab bag. I guess we're a little bit on the on the ordered side of things, but not quite, right? Because we have our Uranus and Neptune, which are quite a bit smaller, particularly by mass, than Jupiter. And of course, Jupiter is interior to Saturn, by which Jupiter is quite a bit bigger by mass, not necessarily by radius, but by mass. So we're actually in the mixed bag. So was that common? It turns out not. So what you want to pay attention to here are the orange bars. So that one, and that one. And these are just histograms, so how many counts of these planets you see, essentially, right? And the reality is that almost everybody is either the same type of planet, similar, or they're ordered, which, to remind you, ordered means little to big, right? So this is really, really jarring to people too. Again, these revelations happened so recently. It's hard to like convey how recently this happened. So, the textbook story that we've been telling for 300 years about everything forming exactly as it is, and maybe like our Jupiters and our Uranuses wander around a little bit. Well, it seems like that story, if it is true, might not be true for everybody because you get very different appearances. And most of the time, by the way, planets are all the same size. They're all basically the same type. And guess, what sort of type do you think that is? Well, it's a type of planet we don't even have in our solar system. It's these weird planets. They're originally called super Earths, which was kind of wishful thinking of an idea. In some sense, people thought, oh, well, great, they're the rocky planets that are just bigger than Earth, and maybe they're even really good candidates for finding life on because they have more surface area. You could grow lots of critters on them. Well, it turns out that those planets really turned out to be a lot closer to what you might think of as a mini Neptune as opposed to a super Earth. Why? Because their cores, let's say their solid surfaces, were still about the same size as Earth at the end of the day. It's just that they had this big atmosphere crunched on top of them. And that was kind of jarring as well. So the story of our solar system started to look more like an outlier situation than anybody had ever anticipated for hundreds of years of thinking about these things within the last 10 years. So this is a pretty big new revelation about how we imagine our own story in the context of this. Now there's one more piece of this puzzle that's kind of interesting, which is there's a phenomenon called a radius valley, which sounds like some scary math or something. But when we look at these populations of planets, they're the most common ones in the whole galaxy, at least according to this preliminary studies. These super Earth planets, which are really more like mini Neptunes, they actually don't appear as a continuum. You find that there's a pretty good portion of them that are like a little bit bigger than our planet, and you have another portion of them that are, say, 3 to, about 3.5 times the size of our planet. But the ones in between tend to be non-existent. Now, what's also kind of interesting is that the further that you find these super Earth planets away from their host star, the more likely they are to be kind of big. So why do you think this is? Yeah.
Because they're not close enough to have their atmosphere be heated off.
Yeah. Well, why would you have two distinct populations? So this is a boss fight question. I've watched them wrestle with this for the last few years, and they've finally got an answer that I think is somewhat satisfying. Yeah.
Based on the things we've covered, if their cores are all roughly the same size, the ones that are the first one are the ones that have had all of their atmosphere blown off and it's now just a rock. And the other ones are the ones that are in the process of it, and there's not very much in between that we can see.
It's something like that. The real trick in understanding this is that if you there's basically a feedback loop that happens, right? So you can imagine that what is this? This is, by the way, this is size, not mass. By the way, this is probably something I should have been really clear about the first day of class. Whenever we talk about something being big, we can mean one of two things. There's a lot of stuff stuffed into a little bit of space, a little volume, or we can mean that its radius is really wide. This is just with respect to the radius, the size of it, right? So you could have something that's actually quite puffy and squishy and light that has a big radius. And that's kind of what's happening here, is that if you don't, at some point, when you're really, really big, you are able to hold on to a lot of atmosphere, right? Your atmosphere contributes to your ability to hold on to more atmosphere. But if that planet wanders too close to its star, or the star is just super, excite, I don't know, what's a good,
Volatile?
I was just going to say, like, just stormy, let's say. It has really intense radiation, X-rays, UV, solar wind stuff. If you lose, some of your atmosphere due to that, well, if you're pretty big, you can probably hold on to a lot of it, actually, it turns out, because you have more pull, right? But at some tipping point, when you lose a certain amount of your atmosphere, it becomes really hard for you to hold on the rest of it, right? Because you don't have the same gravitas that you did when you had all of those extra atoms. And so that was kind of the final solution to this conundrum as to why we don't see those intermediate planets. So a couple of years ago when I was studying this, the leading theory was that the mid-sized ones were crashing into each other and destroying each other in the early development of the solar systems. I think that the reason that one was abandoned is because people started to realize that these super Earth things weren't actually giant rocky planets after all. So they everybody expected that these mid-sized planets were just big rocky planets, but turns out for the most part they're not really. They're just like small versions of Neptunes, which is really, really fascinating. And this should, of course, if you've been paying attention, feed really neatly back into the discussion of the history of Earth that we've been having in the background too, particularly with the two different tectonic scenarios that we explored, right? So there's this Nature paper that came out a couple years ago, which I thought was quite fascinating. This was, by the way, I think this is 2023, so right, I mean, kind of right in the middle of people discussing the new approach to super Earths as well as being actually kind of more like puffy mini Neptunes. But yeah, a group basically proposed a way to get the Earth that we have today, including our oceans. This is an ocean mechanism that has nothing to do with getting pummeled by comets, which was based on the interaction between a hydrogen envelope, right, a primordial thin atmosphere, with the silicate's oxygen-rich mantle. And so I think people have already been thinking about this in other spaces in terms of how the Earth might end up looking the way that it looks as well. So, there's a lot of little pieces of this puzzle that have not exactly found their way to describing how our own planet might form. But it does seem apparent that a lot of these other Earth-like planets are forming by a very different mechanism than the one that we've been thinking has applied to our own planet for all of these years. Questions? Yeah, let's talk about it.
Get my head around what this slide is.
Yep.
Is this basically positing that like there is some sort of metamorphic chemistry happening in the core in the early stages?
Yeah, with its atmosphere, with a very thick atmosphere.
Hydrogen envelope forms around it due to gravitational influence.
It would have been in the model kind of starts with it scooping. Just actually all of the standard for our own solar system, 100% of the planet formation stories start with the solid stuff happening first, and then grabbing up different degrees of the light elements, the gases, the hydrogens, the heliums, stuff like that afterwards.
But for this specifically, there's these later stages where are they saying that basically like the mantle is permeable and is disseminating these heavier elements up to the surface?
Yep.
And then as the atmosphere evaporates or is blown away by solar radiation, that you end up with this sort of rocky body.
Well, yeah, I mean, it was kind of rocky to begin with. By the way, word rocky in astrophysics just kind of means metals.
The elements.
Yeah, because even silicon's a metal, right? I mean, when astronomers and astrophysicists talk about metals, they basically mean all that stuff, pretty much everything, except for, a few of like some gases and some there's a few other families, but the metals occupy the great majority of them, and they're basically just conductive elements, is what it comes down to.
Well, like melting point, or like the point at which the phases like interact.
Yeah.
Too, right?
Yeah, defining metals is actually quite interesting. I realized I just kicked open a hornet's nest right there. I was like, oh god, yeah, what is a metal? We could have a whole conversation about that. The point is, like, they're mostly silicon, silicons, oxygen, nitrogens, nickel, iron, stuff like that. And those, I know you can't see it on this slide, but this paper is talking about all the chemical reactions between those metals and the thin hydrogen atmosphere and how those could result in all of the surface appearances that we see on the Earth today, including the oceans. Yeah, which is fascinating. So, I threw this in there just because I think that it's an example of how kind of where the exoplanetary realization about the mini Neptune transitions, the kind of bridges over to our own story about our own planet. Because, I think the story of us getting pummeled with comets is getting a little bit dated, honestly. I don't know that too many people really think about it that way who are serious. I mean, a lot of people think about the water as being a chemical byproduct of reactions inside of the mantle. I just think that the idea of a thick hydrogen envelope participating in that is kind of cool, especially in the context of that being what we see happening with these transformations that are happening in all of these other, hundreds, if not thousands of other solar systems that we've been scoping out in the last few years. Again, the reason I think this, like, if it sounds kind of disjointed to you guys, that's okay, because it kind of is. This data is so new. We're dealing with a really, really concretized model that has been around for hundreds of years, which is this kind of form in place model thing. These metamorphic ideas are brand new, and so of course people are going to apply them first only to the places where they observe them. I'm kind of inviting you to scope out the future, which might be a little bit different, where we might actually think about our own solar system as having some of these metamorphic processes going on inside of them as well. But yes, Dante is right. The time is always the kicker. But I always, again, I would say that the universe keeps getting older and older, and the bigger our telescopes go. So maybe there will be time to pull off some of these processes in the future. What we do know is that there are a lot of these hot, big, giant planets that are getting cooked out there in other solar systems. This seems to be a super, super common feature of reality, which is that these big planets get pulled in really close to their stars and they get cooked down to something else. And that's just something that wasn't even part of our toolkit until we put these telescopes up and started analyzing really the mass, the density, and the radius. Well, I guess the mass and the radius give you the density. So really once we started to consider those things, it was the first time we were ever even able to consider that processes like this might be taking place. I mean, there's secondary evidence that you can actually see the streaming tails of these atmospheres flying away. Again, I'm not going to tell you how that's done because we do it next semester, and it involves a somewhat complicated astronomy tool, which is called radial velocity measurements, and I don't want to do that. All right, questions at this point? Thoughts? Other solar systems, Neptunes, Earths, super Earths. What do you guys think? Talk to me.
So we talk about star formation and planet formation as these two different processes, right?
Sorta, yeah.
I mean, at least in the late stage,
Yeah.
right? But if going back to that previous slide, if you have these cores that form that create these sort of energy producing and this sort of chemistry that's happening at these high pressures, and then you have this hydrogen envelope forming around it, at what point do you say, like, well, if enough of a hydrogen envelope forms around it, create enough pressure, and then you end up with a star rather than a planet?
Like, what determines the threshold?
Yeah, like
Yeah.
you're saying, it comes down to a single atom, right?
I mean, yeah, I think that, yeah, I need to develop that thought experiment a bit more. I mean, even if it's not, like, there might be ways that someone would say, okay, well, a single atom wouldn't do it because, it's going to have ways of, like, adding that motion into convection or something. It might be,
Even if it's not a single
yeah.
there's some
Yeah. Yeah, it is a threshold. It is, absolutely. And the thing that encourages me about that idea the most is those free floating pairs of Jupiters. I was already kind of like hot on this by the time they were discovering that, but I saw that and I was like, oh man, this is really interesting, right? Because first of all, there's tons of these. They immediately they turned they looked at them and they found, you know, dozens of pairs of these in one little piece of the sky. They were looking in this star forming region nonetheless.
Exactly.
So, you know, I guess the model that I'm going to start really, you know, there's two possibilities here. One possibility is that, yeah, the stars form, and as the stars are forming, the planets are forming through very similar processes, right? They're all kind of congealing out of the same swirling mess. Another possibility is that stars and planets form through very similar processes, but not always at the same time. That's a really interesting idea. That's, by the way, not heretical either. So when people are examining these jumbo things, these Jupiter mass binary objects, you know, people have toyed. This is a fun one too. If anybody doesn't have a final project yet, compare the different theories for jumbos. Right? People get what is it, blue in the face over this. So some people are like, well, they're cast out of solar systems, so those planets formed same as we always thought planets formed, right alongside their star from the same swirling dust gas vortex thing. Some people say, no, maybe they're essentially failed star systems. In other words, they formed just like a binary pair of stars, but they didn't have enough stuff to make a star.
Right.
They didn't accumulate enough stuff to make a star. That's a really interesting possibility to me because what it says is that, you know, while the story that, you know, well, let me back that up a little bit. One of the most troubling pieces of the story of everything forms in place by itself, for me personally, is that it seems like an enormous backflip to explain how you get the first thing that's made in the solar system, other than the star, is the most dense object in the solar system. Especially in light of the fact that it's very difficult to stick pebbles to each other without having them bounce off each other, right? So you have to come up with all of these just so stories where you have like a big thick pile of gas that's slowing everything down and it just drifts together and it's like, look, could it be done? Maybe, but I don't like it. It seems like a very, very tenuous story that was kind of penciled in because nobody could think of anything better. However, if the reality of the situation is that these big condensates like Jupiter's, which, like, let's be completely clear, are basically droplets of stuff from these star-forming regions. If you get little droplets that form as natural condensation reactions, cooling reactions, essentially, and they get big enough, well, they might be able to start to rain out their metals and rain out their silicates and all of these things that we associate with cores. It might actually be possible to kind of condense this nice little droplet of heavy stuff and actually make a little core inside of it. Now you got a core all of a sudden. That's fantastic because you have a reasonable place with extraordinary pressure that would work as a great furnace to make something super, super dense out of. I like that a lot personally. And like, it's just my opinion, and other people like it too. I'm not alone on this. The alternative, which is kind of crashing little pebbles together in the circumstellar disk during the formation of the star, it just you know, and you're, you know, if you want to do your project on this and fight back the other way, I'd be happy to listen. I'd love to be talked out of this opinion too. But just seems like giant planets, especially Jupiter's, you know, they're perfect little furnaces for making the kind of things that we're standing on right now. And you know, maybe Neptunes as well are very similar. Maybe Neptunes evolved from Jupiter's. Maybe they don't need to. Maybe they're perfectly capable of accreting the same stuff at their core as well. Yeah,
Isn't everything in the universe in motion,
sure.
right? Like even our star is orbiting in the galaxy.
Yeah,
right?
Yeah, of course. Really fast. Yeah.
So then that always confused me when they talked about things forming in place. It's like,
Mm,
well, if
mm.
everything's moving, how did they get to forming
Yeah, well,
specific little places in their orbits and those
yeah.
change?
Yeah. Well, yeah, it's tricky. I mean, yeah, humans, this is one of the worst things. It's like, any of you guys have a friend who's a lawyer?
Well, the grandfather.
I got a friend who's a lawyer. Um, my wife probably could have been a lawyer. Look, humans can argue insane stuff, especially if they're really smart. Like, just because you can win an argument doesn't mean you should win an argument. Let me put it that way. So, just because you can come up with a mechanism for how you would get past this pebble boulder problem that I'm pointing at, I believe you could make you could make that argument if you were smart. And some people have tried, to varying degrees of convincing the community about that. You could also make an argument that cigarette smoking isn't bad for you, like Philip Morris did in the Supreme Court. Like, you can do that, and you can get away with it, even though it's just stupid, right? So, your ability to make an argument doesn't necessarily mean that you're right about that. And oftentimes, the more simple, parsimonious explanation turns out to be true. Does it really matter uh, how planets are formed or how cores are accreted or something? I mean, that's what's kind of fun about this class is like these topics we're talking about. They're pretty detached from reality in some sense, but it's also a great exercise in making sense of reality, which is useful for whatever you do with your lives. So I don't know. I mean, I think being able to tell a rational story that we can all get behind about anything in the natural world is a healthy exercise for our species. I just see this as the next iteration of that. But I guess at the end of the day, if this story changes wildly, I suspect it will, from the one that's in the textbook, uh, it wouldn't be that crazy because, like I said, all of this stuff, all of these revelations are a decade or maybe 15 years at this point. They're really, really young. We really were basing everything we knew about planetary formation off of our own solar system. And honestly, the guys who came up with the kind of floorboards of that story, they were basing it off of staring at swirling nebula in the sky, which they thought were planetary systems that were forming. Guess what those turned out to be?
Galaxies?
Yeah.
No, yeah.
Yeah, so, you know, I don't think that hmm, I don't know. I wish there was less shame in changing our minds a little bit about these things. It's often quite painful to do this, but and I think that it's great that all of these people along the way have come up with, pretty good stabs at what could be the explanation for this, that, or the other thing. Given what they knew, I think they were pretty good ideas at the time. Yeah.
Um, Multiple times in this class, we've mentioned how things that are incredibly cratered must be incredibly old, generally.
Well, unless all the cratering happened one day, which is the standard story, basically. Yeah.
Yeah, that doesn't really make much sense because what caused all those things to come?
It's kind of like the ocean being made out of comets. Yeah.
I, but I
Sorry,
was,
is one day specific?
Sorry, I meant like one geologic day. Sorry, the equivalent geologically speaking. Yeah, no, yeah.
but no, I was thinking though because about Earth, many many people don't realize how often Earth gets hit with stuff. We get hit with asteroids all the time.
Yeah, every day.
Every single day. Um, but they almost always end up in the ocean, and it's like, well, yeah, they cover
Or the atmosphere.
planet,
Yeah,
the ocean, and that is the atmosphere. But if they don't burn up there, then they hit most of the time they hit the ocean
sure.
because that's most of them.
It is true. Yeah.
So I was thinking that might be why, because I've heard the argument, well, if Earth is really older, it would be more craters.
Mm.
But I'm like, well, most of the craters would probably just be where most of the stuff is.
Well, not only that, but I mean, we have an incredibly active bio layer on our planet, right?
Yeah.
So this often occurs to me when I go out to the woods because my parents live in Arizona, and it's actually like the rocks and everything are actually quite similar to where I go in the woods out in the Kalmiopsis here. The only difference is we have trees. And what do trees make? They make leaves. And what do leaves make? It makes dirt. And there's animals. And so you have this like very rich remodeling that's always happening of the land on Earth, right? Whereas, on the moon, there's nothing going on. Something crashes into it, it's going to be there until something paves over it,
The
essentially.
same is true for the ocean floor too, because any craters that are on the ocean floor, well, the basalt
You get smoothed over there.
just go under continents.
Yep,
and
yep,
get recycled.
yep.
They're only, the ocean floor is only a couple 100 million years old.
Yeah,
That's
that is really nuts. Yeah, at its oldest.
it's fascinating that you brought up the biolayer too, because like one of the things that's being done in desert areas for reforestation is they're effectively making craters that create shadows during certain times of the day to allow
Interesting.
condensation, to allow the water to stay in the surface or in the soil for long enough to
Grow stuff.
facilitate more growth.
Yeah.
Right? And so it's funny that you mentioned this, the biolayer, because like, oh yeah, you would end up with larger areas of biodiversity in an area that's creating more shadow, right?
Yeah, the feedback loops are pretty insane when it comes to the way that life remodels. Well, just in general. I mean, feedback loops are a huge part of the way that things look the way they do. That's what that whole radius valley story that I tried to tell you was about too. It's like when you cross a certain tipping point, then you're going to accelerate processes that drive you into one bin versus the other. The same is true with why do we sometimes have big glaciers covering our planet? It's like, well, once you get a little bit of glacier, then it starts reflecting the sunlight. Then it gets really cold, and like you have these tipping points that'll just, yeah.
I'm reminded a bit of when we talk about how we sort of think that what we see in the present day must have, there's this idea that what we see in the present day must have been what it was like in the past,
Yeah.
that sort of conflation. And it's funny because we do this not just on this macro scale of planets, but we also, I remember seeing people, they did it with our own human culture.
Yeah, yeah.
Right. um there's
It's called
I remember
uniformitarianism.
I
Yeah,
read a paper about
gradualism.
the discovery of the likely candidate for the Pichon River, which is mentioned in the early Jewish Bible.
Okay.
Basically, and now it connects into Mesopotamia, the two rivers there, and the third one, the Euphrates, the Tigris. Those are mentioned. We know that those rivers are the ones that were right. Those ones were already okay.
All right.
Right. But we were looking for this fourth one because it's like, well, it's mentioned, but it doesn't exist. And when we found what it would be, it was massive because it was almost 2 miles wide.
Is it gone or is it
It's
underground?
It's
Yeah.
completely gone.
Okay.
It's just, but you can see where the rocks went from mountains and got eroded, and you can remember you see that. But they only discovered that once they gave up the idea that, well, the Mesopotamia must have been a desert back then.
That is one of the hardest things to understand. It's so funny because I remember learning that the cradle of civilization was in Mesopotamia when I was a kid, and I was like, doesn't seem like a reasonable place to start all of this at. But yeah, it was a beautiful, beautiful place back then. I think Egypt was too at some point in its classical heyday as well. Yeah, it's really hard for us to understand. I think also because this last generation has been obsessed with human-driven climate change, which, power to us for taking care of the planet, but it obscures the fact that every civilization has suffered climate decline. All of them. In fact, I would say it's probably one of the main drivers of why civilizations collapse historically, and it has nothing to do with the fact that they didn't have catalytic converters or something. It's just that that's how the Earth works. It's always changing, and it's not easy for people to hang with the fact that it changes constantly. So it'll be really interesting. We're, uh, yeah, climate scientists don't probably want to talk about this, but we seem like we're on the edge of going into another ice age at some point here, at least in the next few thousand years. Could be tomorrow, could be a few thousand years from now, but that'll be really interesting, right? That'll be interesting how we handle that. Maybe, yeah, who knows? I mean, historically, it seems like people just move. They just go and start cities in places that work out a little bit better. But who knows, you know? I do know that change is coming, and we will have to adapt one way or the other. All right. I think I've set everything up to compare these. Oh, I do want to talk about one last thing before this will cue us up for our last class, where we'll kind of compare and contrast the whole stories, two possible stories here for the solar system. Why do people think that the Earth and everything in the solar system is only 4 billion years old?
Carbon dating?
Carbon's not great. Its half-life is more appropriate for things in the recent past. But yeah, radiometric dating is what it is. So that's often the thing that people point to. Now, of course, that might not even be the first thing they point to. They might point to formation models and stellar models and models and models and models all the way down. And that's fine. But when it comes down to like the cold hard facts of the Earth is 4 billion years old, plus or minus whatever, and so is every other rock that we've ever measured. What do they mean? They mean that when they do this radiometric analysis, they get this age of around the oldest age that they've ever gotten from any of the rocks that we've ever looked at in our solar system. Asteroids, comets, pieces of Mars, pieces of the moon. There's 2 really old rocks on Earth. There's only 2 of them, by the way, that are on the order of 3.8 billion years old or something like that. Nobody's ever gotten past this 4-something billion year old mark, right? How do they know that? How does this work? Can anybody tell me how this works really quickly? Yeah.
I believe they look at how the deterioration of
How,
radio.
how does that work as a clock?
Well, the more deteriorated something is, usually the older it is.
Yeah, so basically all rocks are made out of atoms, and certain atoms have a really predictable rate at which they break apart into smaller atoms, right? This is just called nuclear fission or radioactive decay, right? So what they'll do is they'll basically compare the amount of the fresh stuff that hasn't broken up yet to the amount of its daughter products that are inside of the same rock sample. And they essentially fit it on a curve like this, and they'll say, well, like half of the original stuff has disappeared, therefore it's this many half-lives old, because we know the rate at which it decays, and we get a date for it. Seems like a pretty freaking awesome scientific measuring stick, right? What could possibly go wrong?
Well, what if the stuff is doesn't radioactively decay? Like it decays faster than it like the actual like origin of say a planet.
That's it. That's a reasonable concern. There was a Stanford geophysicist, I can't remember his name right now, I think it's Sturrock. He's retired or dead, but he has written extensively on the fact that radioactive decay is deeply dependent on cosmic processes like the solar wind, the sun cycles, stuff like that. So that's a real possibility. The rate of decay isn't constant. How about that? Certainly does seem to be a serious problem. But what else? What else could totally screw this up for you? Yeah.
Everything got melted at some point.
That's a big one. That's a really, really big one. So all it can tell you is it can tell you the last time that fresh mother nuclei, the stuff that hasn't decayed yet, it can only tell you the last time that the whole thing was fresh, right? So if you melt a rock, you introduce new, fresh, heavy elements into it from the atmosphere, from the cosmos in general. So the problem with the pointing at this as some sort of absolute dating metric for the existence of a rock is that it doesn't really tell you how old the rock is. It just tells you the last time that it was melted and incorporated fresh stuff in. So that's how we end up with this dates. Everything that we've ever measured was at least melted 4-something billion years ago. And that's kind of the lower boundaries on this. The rest of it comes from modeling, cosmological constraints, things like that. So I think with that in mind, we're ready to piece together a story of our solar system once and for all. Otherwise, yeah, have a good week. Don't stress out about your finals and stuff. I hope it's, I'm sure you guys will do great. And we'll put a bow on this thing on Thursday.